Hello and welcome back. In the next several videos, we'll be discussing a series of topics which typically fall under the category of semi-classical physics. And basically what semi-classical physics is this is a term which we use to describe the advancements that were made in the very early part of the 20th century, where physicists attempt to explain these very strange phenomenon in terms of very classical ideas. Ideas like the idea that a particle will exist at some point in space and have an exact position. And one of the things that I should point out about these ideas in semi-classical physics is that semi-classical physics is really a phenomenological area of physics where a lot of these theories attempt to explain very specific phenomenon, and they cannot be very easily generalized to explain a wide range of phenomenon. Nonetheless, these ideas in semi-classical physics really represent the very first steps towards developing these more modern theories in physics, ideas like quantum mechanics and relativity. And so, even though none of these semi-classical ideas are completely true or represent the most contemporary understanding, these are still very important first steps towards understanding these more modern theories in physics. So everything we've talked about in this class up until this point has been part of what physicists would call classical physics. So things like Newton's law, work energy, impulse momentum, thermodynamics, electricity, magnetism, and waves, all of these are classical ideas. And basically, what I have shown on this slide represents where physics stood at the middle of the 19th century. And so it's sort of like the last ideas that people had figured out was electricity and magnetism were sort of finally hammered down in the 1860s and 1850s. And statistical mechanics, which we've touched on briefly when we talked about entropy, and I talked about how we can describe entropy in terms of these microstates and macrostates. Well, statistical mechanics attempts to explain the relationship between things like pressure, volume, temperature, and atom number in terms of these microstates and the probabilities of being in different microstates. And statistical mechanics was probably one of the last classical ideas to be developed. This was developed in the sort of later 1800s, 1870s, and 1880s. Obviously, the big obstacle towards developing statistical mechanics is understanding and appreciating the idea that everything is made up of these atoms. However, the thing that I really want to focus on right now are the advancements that were made in the middle of the 1800s towards developing our understanding of electricity and magnetism. So in the 1860s, a man named James Clerk Maxwell made a very important discovery that basically directly led to the two founding theories of modern physics. These are Einstein's theory of relativity and quantum mechanics, and we're going to mostly focus on the latter of these two theories. Now, for those of you who will be sticking around after the AP exam, I'll talk a little bit about Einstein's theory of relativity during those last couple of weeks. Recall that when a coil is placed inside a changing magnetic field, the changing magnetic flux through the coil will induce a current inside this coil. So for example, here I have a coil which is placed inside a region where there is no magnetic field. And if I suddenly turn on a magnetic field that points out of the screen, then this coil is going to try to create its own magnetic field which opposes the change to the magnetic flux. So, for example, in this case, because we're turning on a magnetic field which points out of the screen, the coil will attempt to cancel this by creating its own magnetic field that points into the screen. And to do this, the current will flow through this coil in a clockwise direction. Now, one really important concept which I tried to emphasize when I introduced this idea of electromagnetic induction is that a changing magnetic field actually creates an electric field. So this changing magnetic field all by itself creates an electric field, and it's that electric field that is creating the current inside this coil. And the important thing to understand is that this electric field would exist even if the coil wasn't there. So if I suddenly turn on a magnetic field, that changing magnetic field will actually create an electric field which is going to point in this direction. And that electric field exists even if there's not a coil there to feel the effects of this electric field. And this concept is explained in this equation that I have written here. So we would say that the curl of the electric field is equal to minus the derivative of the magnetic field with respect to time. And this thing over here on the left, this is called a curl, and it's this idea in vector calculus, and basically it describes exactly what you would think it would describe. It describes the tendency for a field to kind of go like this, to have these sort of circular path like this. So this is kind of what a curl describes. It describes a field that's doing this. So we're saying that when you change a magnetic field, you create an electric field which goes around in a circle. And we call this phenomenon electromagnetic induction. However, it turns out that this equation doesn't give us a complete understanding of electricity and magnetism. In the middle of the 1860s, James Clerk Maxwell basically discovered that our understanding of electricity and magnetism was inconsistent. In other words, he found that he could do a calculation 2 different ways and get 2 different results. And to fix this, Maxwell had hypothesized that a changing electric field could in fact create a magnetic field in a very similar way. So if I change the electric field, I'll create a curl in the magnetic field. And this is very important because what this means is basically Maxwell was showing that there are 2 ways that you could create an electric field and 2 ways you could create a magnetic field. So, of course, an electric field can be created by a point charge, but we also know that an electric field can be created by a changing magnetic field. That's what electromagnetic induction tells us. And we also know that magnetic fields can be created by moving charges. However, James Clerk Maxwell hypothesized that magnetic fields could also be created by changing electric fields. And what this means is that if you're very, very far away from any charges, you can still have electric and magnetic fields, because if you have a changing electric field, that changing electric field will create a magnetic field, and that changing magnetic field will in turn create a changing electric field. So you'll have these changing electric and magnetic fields that'll be driving each other. In fact, if you think about this, we now have 2 equations which describe the interaction between electric and magnetic fields. So if we want to, we can combine these 2 equations and write down an equation that just describes the electric field and another equation just in terms of the magnetic field. And this is exactly what Maxwell did. And when he did this, he immediately realized that the resulting equation was just the wave equation. So this is the same equation that we use to describe waves on strings. So this meant that electric and magnetic fields were actually waves. So they'll exhibit all the same wave phenomenon that we've talked about before, like interference and things like that. And one of the important things to know about the wave equation is that the speed that a wave is moving actually appears as a constant inside this equation. So when Maxwell calculated this value, he found that the waves that are produced for magnetic fields and electric fields both move at the same speed, and that speed is equal to the speed of light. Now, of course, at this point in time, people already knew that light was a wave. Thomas Young had already done his double-slit experiment, so people knew that light was made up of some type of a wave. And now Maxwell discovered that electric and magnetic fields behave as waves and that they travel at that same speed, the speed of light. So this really showed people that light was actually nothing more than an electromagnetic wave. So now that physicists finally understood how light was actually created, many of them had hoped that they could use this understanding to explain several of these unsolved problems in physics. And the 3 problems that I want to talk about are the Blackbody problem, the photoelectric effect, and the atomic spectrum. And in this video, I'm really going to focus on the Blackbody problem. And before I talk about this too much, I want to just remind you what the blackbody actually is. So remember earlier in the year when we talked about heat transfer, we said that there were 3 different ways that heat can move from one place to another. There's convection, conduction, and radiation. And recall that convection occurs when fluid that is carrying heat physically moves from one place to another. So for example, when the temperature outside changes because a cold front or a warm front moves in, that's an example of heat that's transferred through convection. Conduction, on the other hand, occurs when heat is transferred between 2 objects which are directly in contact with each other. So for example, when you place a pot of water on a burner on the stove, the heat is transferred from the burner to the water through conduction. And the final form of heat transfer is radiation. And remember, this is the idea that, any object, whenever it's heated up, that object will emit some light, and that light carries with it heat. So the idea behind the blackbody problem was to explain, well, first off, why is it that a heated object emits light? And the second question is, why does the light change color? So for example, if you heat up a piece of metal, it originally starts glowing this very dull red, and as you heat it up, it begins to glow a brighter orange, and then finally this really bright white color. So why does that color change, and how do we explain the brightness of these different colors that are emitted by an object as it's heated up? And we use this term black body to describe an object which perfectly absorbs or perfectly emits light. And we call this a black body because an object which perfectly absorbs all of the light that hits it would appear black, because none of that light that hits the object would be scattered off. And in particular, in the black body problem, we're looking at the light that is emitted from a perfect black body. Now, at first, Maxwell's equations seem to provide the perfect explanation behind blackbody radiation. So the idea is that if I have some piece of metal and I start heating it up, well, recall that we can treat a piece of metal like a box that's holding these electrons, and these electrons can just bounce around. Well, as the metal heats up, these electrons move faster and faster, and they're bouncing around. Of course, the electrons create an electric field because they're a charged particle, and they create a magnetic field as they move around. So these changing electric and magnetic fields caused by these electrons bouncing around should create light. And in the early 1900s, a man named Rayleigh attempted to use this explanation for blackbody radiation to try to derive a formula which would describe the amount of light that's emitted at different wavelengths. And basically what Rayleigh had discovered was that the amount of energy that's emitted over a range of wavelengths, delta lambda, for an object which is at a temperature T, is given by this formula right here. However, there were two major problems with this formula that Rayleigh had derived. The first is that this result didn't actually match the experimental results. So people had measured the intensity of light that's emitted at different wavelengths, and it didn't match this formula which Rayleigh had derived. The second major problem is that the total energy that's emitted by an object can be found by summing this up over all of the ranges of wavelengths. So we can do this by taking an integral and summing this up for wavelengths from 0 meters all the way out to infinity. And when you do this, you find that the total energy that's emitted by an object is going to go to infinity, because it got this 1 over the wavelengths to the 4th power. So obviously, this result just violates everything we know about energy conservation. And this was called the ultraviolet catastrophe, because this integral here blows up when the wavelength becomes very small, so when the light goes into that ultraviolet range of the spectrum. So what do we do now that our theory gives us this wrong answer? Well, the obvious thing to do is just to go ahead and measure the amount of light that's emitted at different wavelengths from a perfect black body. But how do you actually create a perfect black body? Well, the answer is that you take a large container and you drill a very small hole in the container. And the basic idea is that if light shines into this container through that hole, that light's going to bounce around many times. And every time the light bounces off of the surface, some of the light is absorbed by the walls of this container. So the light comes in, some of it's absorbed by the container, and some of it gets reflected. And then some of the light gets absorbed by the wall again, and some of it gets reflected. And because the light's going to bounce around many times before the light escapes through this hole again, almost all of the light that shines into this container is going to be absorbed by the walls of the container. Similarly, when the walls of the container emit light, that light doesn't fly directly out of the hole. So a point on the wall here might emit some light that's absorbed somewhere else in the container, and then that's going to emit light that's also absorbed elsewhere in the container. And what this means is that the light that's emitted through this hole is going to be the same as the light that's emitted from a perfect black body. So basically what you do is you heat up this entire container, and as you heat up this container, light will begin to emit from this hole. And if you pass this light through a prism or a grating or something that's just going to split up the different wavelengths of light, you can then measure the intensity of the light at the different wavelengths. And this is exactly what physicists did. And they discovered when they measured the intensity of the light that's emitted from the black body, they found that this actually decreases for smaller wavelengths, so it doesn't blow up like this classical equation gives us. In fact, they had found that the energy went like 1 over the frequency squared for very low frequencies, and then it decayed exponentially for high frequencies of light. So how are these experimental results finally explained? Well, as any good physicist will tell you, once you know the answer to a problem, it's really very easy. All you have to do is work backwards. And that's exactly what Max Planck did. So in 1900s, Max Planck was studying the entropy of the light inside a container like this. So in other words, he was looking at all the different ways that light could be emitted from the walls of this container and still have the same macro state. And in particular, Planck was focusing mostly on light that was emitted at high frequencies and low frequencies, because this is the area where the experimental results were very, very clear. So what Planck did was he used those experimental results to calculate the entropy at high frequencies and low frequencies. So he found 2 different formulas, one formula that worked at high frequencies and another formula that worked at low frequencies. And at this point, basically what Planck did was he just guessed at a formula that would work at high frequencies and also work at low frequencies, because he knew what the answer needed to be at high frequencies and he knew what it needed to be at low frequencies, and then he just kind of said, well, I need the answer to have these properties, so I'm just going to guess something that has those properties and we'll see what that gives me. So once he guessed a formula for the entropy, he then started to work backwards and calculate the amount of energy that's emitted at different wavelengths. And he then compared this result with the experimental results. And when he did this, he found that they matched perfectly. So Planck knew that his formulas were right because they perfectly matched the experimental results. But he couldn't find any good explanation for why his formulas worked. After all, in the end of the day, he really just kind of guessed a formula for the entropy. So looking for some kind of good explanation, Planck turned to statistical mechanics, and as he started to work through the statistical mechanics calculations, he discovered that his formula was equivalent to assuming that the energies that were absorbed and emitted by the walls of the container always occurred in packets of energy that were given by this formula right here. So the light that was absorbed and emitted by the containers of the wall were always absorbed and emitted in packets that had energy equal to some constant times the frequency of that light. And this constant is now called Planck's constant, which has a value of 6.6 times 10 to the minus 34 joules seconds. And one of the things that I really should just point out about this result is that at the time when Planck had made this discovery, most people thought that this was somehow a property of the black body, that the actual walls of this container, for one reason or another, just chose to absorb and emit light in these types of packets. So this wasn't assumed to be a property of light. This was assumed to probably be some kind of property of the actual black body. And so this result all by itself doesn't really prove the existence of photons, which we're going to talk about a little bit later, but it was a very important first step towards developing this photon explanation. And in particular, in the next video, we're going to talk about another phenomenon called the photoelectric effect. And this was a very, very important experiment because this really was the next step towards understanding how light actually works.